In this video, I will introduce you to some additive synthesis implementation techniques. Probably the way to begin with additive synthesis really proceeds from the idea of a spectrogram. You might say, I want the sound to have a spectrogram that looks like this, for example. So we could say that it has a number of partials. Maybe they do some sort of vibrato or other behavior later on. But really, you think of it as you have these trajectories in frequency, typically, and you want to figure out how to implement each one of those trajectories. Now, specifically, I'll focus on the partial that has the lowest frequency here. So we think of this as having two aspects to its behavior in time. The first is how the frequency varies in time, and the second is how the amplitude varies in time. And my recommendation is that you always have the frequency remain at some non-zero value, and then you use the amplitude to indicate when that partial begins and when the partial ends. If you actually set the frequency to zero itself, that can cause various types of discontinuities in your sinusoidal oscillator results that give some undesirable effects. Now, if we turn our attention to the next partial, we see that this has a higher frequency. It's more or less constant throughout time, and it starts a little bit later and ends earlier. So we then shape that sinusoidal oscillator output with an amplitude envelope such that we cause the partial to die away earlier. And again, you can adjust the amplitude as needed. It doesn't always have to be at 1. It can be something less. Now, let me talk about the design of the amplitude trajectory, and it works best if you begin by designing the intensity or loudness trajectory, and then you convert that to amplitude. So we're going to focus on how you want the ear to perceive the sound. 0 dB corresponds to the maximum volume, or the maximum amplitude ultimately, and minus 40 dB or possibly minus 60 dB is soft enough to be taken as silence. So 0 dB ends up being our loudest possible signal. Now imagine that we wanted the loudness to be silent for a while, linearly increase up to the maximum value, and then linearly decrease back to silence. So it's probably easiest for us to work with these straight line segments when implementing the trajectory, the intensity trajectory. And then to convert that to an amplitude, well, we can undo the decibel equation and divide the intensity by 20, and then use that as the argument to the exponential, or as the exponent of a power of 10. So that then becomes our amplitude trajectory. Similarly, if we want to design the frequency trajectories in a way that we end up with something that sounds musically interesting, we might work in so-called octave space, and then we can convert that to the actual frequency in hertz. So in terms of working with octaves, you might think about the idea of an interval, and an octave is a 2-to-1 interval. So you might say that 0 corresponds to our nominal frequency, or reference frequency. Or we could also call that our reference pitch. Then 1 would correspond to an octave above. 2 would correspond to 2 octaves above. And of course, -1 would correspond to an octave below the reference pitch. So in this way, we can draw a trajectory that will sound kind of like what your intent is. So you might say, I want to start at a reference pitch and perhaps do something that sounds somewhat like a chromatic scale going up 1 octave, maybe a little bit quicker up to the next octave. You can do really whatever curve you like, even things like partial octaves, and so on. So you kind of trace out how you want the ear to perceive that signal. Now an octave is a 2-to-1 interval. That's its basic definition. To convert the octave number to frequency, we say take your reference frequency or your reference pitch and you multiply that by 2 raised to whatever you're calling an octave space. I'm calling it F sub OCT, and that's it. That's how you convert the octave trajectory into frequency in hertz. Notice that if you apply some test values like, say, 2 octaves above, you see that would be 2 squared. That'd be 4 times, so that would be 2 of our octave intervals. It's a very simple equation, and again, my recommendation would be to do the design first in octave space and then switch that back to frequency.